So this is Yadagiri, working as assistant professor in EEE department in Marri Laxman Reddy Institute of Technology and Management. So today I am going to give the lecture on electrical circuits 1. So today's my topic is energy sources and source transformation techniques. So energy sources are classified into two types. So that is the energy sources are DC sources and AC sources. So DC sources are again divided into two types. So they are dependent sources and independent sources. Anyway, the DC sources are not categorized in any classification. So here we can see voltage source, and we can represent this voltage source in this fashion, and the current source we can represent in AC circuits. We can represent these are the energy sources or the voltage and current sources. So coming to the DC sources, so dependent sources and independent sources. So dependent sources are again classified into four types. So they are voltage dependent voltage source, voltage dependent current source, current dependent voltage source, current dependent current source. So independent sources are again classified into two types. They are ideal sources and practical sources. So here again ideal sources are divided into two types. One is ideal voltage source and another one is ideal current source. Similarly, the practical sources are again divided into practical voltage source and practical current source. So this is the classification of energy sources. Now let us discuss one by one. So what is the dependent sources and what is the independent sources? So first we will discuss about the independent sources, then we can go for the dependent sources. What is meant by independent source? So independent source means the voltage or current is not dependent on the others, not dependent on the other elements. That is, in the same circuit, the voltage and current is not dependent on the other parameters like in the resistor or inductor or capacitor. So they are not, the voltage and currents are not dependent on the same circuit. So then that circuits we can call it as independent source. The independent sources. That means that source, whatever the source value, either voltage or current, it is not dependent on the other values, other parameters. So then we can call that as an independent source. So we can see the definition here. What is independent source? So voltage of the voltage source is completely independent source of current, and the current of the current source is completely independent of voltage. Then the sources are called independent sources. For example, we can see here. So for example, if you can take one voltage source and simple circuit I am taking here. So this voltage source is not dependent on the other voltages. It is not dependent on the other networks. Like it is not dependent here. It is not dependent here. In this resistor, it is not dependent. So it is not. That means here, this source we can call as independent voltage source. It is not dependent on the other parameters. So either you can say voltage or current. So it is independent of the circuit. So now coming to the next one, that is dependent sources. So dependent sources is a special kind of sources, so which may depend on other parameters. So which the source voltage or current is depends upon the some other quantity in the circuit. Some other quantity in the circuit means whether it may, these voltages are dependent on current or current may be dependent on voltages. So which may be either voltage or current anywhere in the circuit. Very, very important point is anywhere in the circuit. So within the circuit, we can simply say within the circuit, then that type of sources we can call as dependent sources or controlled sources. Dependent or controlled sources. So now let us see the different types of controlled sources here. So first one we can see the current dependent current source. So this is the within the network we can consider here. So this current flows into this network. So let us take this is completely we can take as one complete network. So in this network, so it is a this current is depends upon the other parameters. So that is we can call current dependent current source. So this current is depends upon the within the same circuit. So we can call this current dependent current source. Similarly, if you can take this complete network, so here this voltage is depends upon, so this source, whatever the source is there, this is the current source. This current source is depends upon the voltage. So that voltage is within the circuit only. Similarly, we can see here. So this is the current source. This source is depends upon the current in the within the circuit only. So that's why it is called current dependent current source. Similarly, we can see for the second diagram. So here, this voltage, this source, that is current source, is depends upon the voltage. So it is called as voltage dependent current source. Similarly, we can see for the third diagram. So here, this voltage source is depends upon this voltage within the circuit only. So that means here it is voltage dependent voltage source. It is voltage dependent voltage source. So that means this source is depends on this voltage within the circuit. Whereas in case of independent sources, we can see the sources are not dependent on the other branch voltages or currents. Okay, so here especially in case of dependent sources, they are dependent on the voltage or current in the same network. So that's why these sources are called as dependent sources. Coming to the next diagram, so that is this voltage source is depends upon the current within the circuit. So it is depends upon this current. So that's why it is called as a current dependent voltage source. So that means this source is depends upon current within the network only. So these are all called as a dependent sources. So current dependent current source, voltage dependent current source, voltage dependent voltage source, and current dependent current source. Now let us see the what are the units for this. So here the proportionalities were given for BGAR. So we can see the proportionality constants here. So the proportionality constants, we can take this for 4 diagrams. So you can see the proportionality constants here. So first one you can see, so it is B, G and A and R. So these are the proportionality constants. So now we can see the units for this one. So it is a current dependent current source. So there is no units for this B. So B has no units because it is depends upon the current. So if you can take the ratio of that one, the current divided by current, will get the no units. Will get cancelled, then no, will not getting the no units. Similarly, R has units of ohms. So you can see here. Similarly, R has units of ohms and G has units of mho. So we can see here, so this G has units of mho. Okay, because it is a voltage dependent current source. So if you can take the ratio, so that is this current is we can say that the current is directly proportional to G into V. So from that, so current we can take as G into V. So from that, G is equals to I by V. So this is the units of mhos. Similarly, R has units of ohm. So that is voltage source V is equals to R into I. So from that, R is equals to V by I. So the units for this one is ohms, and the units for G is mho. So for this we can see the current is direct, the current source is direct is equals to B into I. So if you can take the ratio, then B is equals to I by I, then there is no units for this B. Similarly, if you can see here that voltage source is equals to A into V. So if A is nothing but V by V, so here also we are getting no units here. Anyway, so while solving these problems on the dependent and independent sources, there we can see the more related concepts here while discussing the problems. So here, independent sources, the examples for the independent sources are battery, DC generator, or an alternator. But dependent sources are used to represent the electrical parameters in electronic devices such as op-amps and transistors. So dependent sources we can mostly use it in electronic devices circuits. So independent sources we can use it in the batteries, DC generators, and as well as AC generators. So that is about the dependent and independent sources. So again, independent sources are again classified into two types. Just now we have seen. So that is ideal sources and practical sources. So now we will discuss about the ideal and practical sources. So what is meant by an ideal voltage source? And what is meant by an ideal current source? So you can see the diagram here. So this is the representation of ideal voltage source. The circuit for this one, this is the ideal voltage source. Ideal voltage source. And this is a practical voltage source. This is practical voltage source. So this is ideal current source. And this is practical current source. So how we can distinguish this ideal sources versus practical sources? Based on their IV characteristics, we can decide, we can say that we can classify that ideal and practical characteristics. So let us discuss the ideal voltage source first, then we can, after that we will go see the ideal current source. So here if you can connect one load here to these two terminals. So here we can see the terminal characteristics of this ideal voltage source. So these are what are the terminals means here. The current flows to this load is IL, and the voltage across these two, across this element, that is load element, is VL. So here according to the volt ampere characteristics, so that is here the voltage is constant irrespective of this terminal voltage. If you are connecting a load here, so here this voltage, that is load voltage, and this is the load current. So this voltage is constant, that is Vs, the source voltage. So that whatever the voltage we are applied, the same voltage we are getting across these two terminals. So in the ideal case, whatever the voltage we are applied, the same voltage will be reflected across the load or the same voltage will be appeared across these two terminals of the source, so which is connected to the load. So therefore the voltage source is equals to, that is VL is equals to Vs, that is load voltage is equals to source voltage. So here, irrespective of the load current here, so that means here, even if the current is increased here, so then it is not a problem here. So the voltage is maintained as constant across its terminals. So such type we can call it as ideal voltage source. So that means irrespective of the load current, we are getting constant voltage across its terminals, then such type of sources we can call it as ideal voltage source, and the such characteristics we can call it as ideal characteristics. So coming to the practical, so here in the ideal case, you can see the difference between the ideal and practical cases here. Here the resistance value is, that is R internal resistance is equals to 0 here, or equals to 0. So that's why whatever the internal resistance is 0, so therefore whatever the voltage were applied, the same voltage will be getting across its terminals irrespective of this load current. Whereas coming to the practical voltage source, so practically every voltage source is having some internal resistance in series with the voltage source. So that practical case you can see in the diagram. So here, if you can connect, if you can take this current is flows to this load. So now, because of that internal resistance, we will check whether we are getting the same voltage Vs or not across this load voltage, across this load or not. So first we will check that if you are getting the same voltage, then it is ideal. If it is not getting, if it any drops is taken place, then we can consider that as a practical. So how it is, we will see now. So first we will see if we can apply the KVL in this loop, because it is a closed loop. So while applying the KVL in this loop, so this is the current flows into this is the source current, this flows into this resistance, and this is the load current. So I can take this, we have to apply the KVL in this loop. So that is IS into R internal plus IL into R. So I can take this as, so we can see here, that is IS into R internal plus VL minus Vs is equals to 0. So from this, what we have to write, so what we want, we required what is the load voltage. So here VL is equals to Vs minus I, so in place of IS into R internal. So that means here, so that is voltage, that is load voltage VL is equals to Vs minus IL into R internal resistance. Since here IS is equals to IL, because both are connected in same connection. So we are getting the, if we are increasing the load current here, so because some drop will be taken place across the internal resistance. So if you are increasing the current, load current, then what happened here? So the load voltage will be decreases here. So that means if you are increasing the load current, then the load voltage will be decreases. So that means we are not getting VL is equals to Vs as in case of a ideal case. So we are getting as VL and some drop. So because of the drop, we are not getting, we are getting the characteristics like this. That is, if you are increasing the load current, so then this is the characteristics we are getting. So these characteristics we can call it as practical characteristics. So this is regarding the ideal and practical voltage sources. Coming to the ideal current source and ideal current source and practical current source. So here also we will analyze the VI characteristics of ideal current source and the VI characteristics of practical current source. So here, if we can connect a resistance across these terminals, so if we can see the characteristics of these terminals, that is VL and IL. Okay, so here whatever the current is, source current is there, the same current is flows into the load irrespective of the load voltage or terminal voltage. Irrespective of the load voltage or terminal. That means here my current is, that is load current is constant irrespective of my terminal voltage. So that is IL is equals to IS. That means source current is equals to load current irrespective of my current. Ideal means whatever the input we are giving, exactly we are getting the same output. So that's why we can say that IS is equals to IL irrespective of the load voltage or terminal voltage across its terminal. So we can call this as ideal characteristics of current source. Whereas coming to the practical current source, so practically every current source having its internal resistance in parallel with the current source, So here the internal resistance we can consider as in the ideal current source is infinity. So if it is infinity means there is no current is flows into this branch, so therefore it is open circuit here. So that's why the current is flows, whatever the current is there, that same current is flows to the load. Similarly, we can see for the practical current source. So this is our load current as usual, and this is our load voltage. So we can see that this current, the source current is divides into two parts here. One is load current and another one is this internal branch, we can say the shunt branch resistance. So if we can apply the KCL here, that is source current is equals to the shunt branch current plus load current. So here the shunt branch current is equals to, or if you can see the load current, so the load current is equals to source current minus shunt branch current. So the source current minus the shunt branch current is the, so this, let us take this V at the point here, so that is VL, or we can say that this is a VL at that node, so VL divided by RS, R internal. So that is nothing but, so here the current is decreases because of the shunt branch. So that means if the voltage across the load is increases, then load current is decreases. That means if between two terminals, if the load voltage is increases, then the load current will be decreases. So that means here, if you are increasing the load voltage here, then the load current will be decreases. So these are the practical characteristics. So from this analysis, what we have to conclude that, so the internal resistance of ideal source is 0, ideal voltage source is 0, whereas the internal resistance of ideal current source is infinity. So this practical voltage source, we are generally ideal voltage sources and ideal current sources are, we are not getting. So practically we will go for the practical voltage sources, practical current sources. So every practical voltage source and current source having its internal resistance. So these are the analysis we have seen. So this is about the ideal and practical voltage sources. Now coming to the different voltage sources. So while solving the different problems, we will get the different voltage sources, ideal voltage sources and ideal current sources. So all are connected in series and parallel. So sometimes they will connected in series, sometimes they will connected in parallel. So different voltage sources are connected. So we have to reduce that into one simple network for simplifying for analysis purpose. So we will see that different cases here. So first one, ideal voltage source connected in series. So we can see if two voltage sources are connected in series, then the total voltage is equals to, that is V1 plus V2. The total voltage across the two terminals is equals to V1 plus V2. Similarly, if we can see the practical voltage sources are connected in series, then we can see that the equivalent of this network, that means whenever the circuit is having such a type of network here, then we have to reduce it into one simple network here. So that is, we have to reduce one single voltage source and one single resistance, that is V is equals to V1 plus V2 and R is equals to R1 plus R2. So that is about the ideal voltage sources connected in series and practical voltage sources are connected in series. Similarly, if you can see for the ideal voltage sources are connected in parallel, so like that, if you can take up to n number of voltages, so that is V1 and V2 across these two terminals, so then what is the final answer here is that, so V is equals to V1 is equals to V2. So in parallel circuits the voltage will be same, so that's why we can take that as V is equals to V1 plus V2. Whereas in case of series circuits, the total voltage is the sum of the voltages, that is V is equals to V1 plus V2. And here in the practical sources we can say that V is equals to V1 plus V2 and the resistances are added up. So that is the difference between the ideal voltage source and practical voltage source connected in series and parallel. Now coming to the next one, that is if the practical voltage sources are connected in parallel, then what we have to do? So here we are going to apply source transformation technique. So before discussing these techniques, we are going to see what is the source transformation technique. So here, so let us take voltage source here. So I am going to take that voltage source. So we have to convert the source transformation technique here. So I am going to teach you that source transformation technique. So source transformation technique is nothing but we have to convert whenever it is required. We have to convert from voltage source to current source and current source to voltage source. So depending upon our problem, we will have to convert that into. So first I am going to take the ideal voltage source. So sorry, practical voltage source. It is having the series resistance RSC, and this is V, capital V, and we are having the current source, that is practical current source. This is having shunt branch resistance, that is RSC. This is I. Okay, so the condition for the source transformation is that we have to connect to the same load resistance between these two terminals, and the current flows to these two terminals, whether we can see the voltage source or current source, must be equal. So this is the condition for source transformation. So that is, the current flows to this branch, that is load resistance. Whatever the current is flows into this branch, that is load resistance, with the help of practical voltage source, the same amount of the current is flows into the load resistance in the, while we are using the current source, practical current sources. So now, so what is the conclusion? So we will see the conclusion here. So first we will see what is the current flows into this circuit. So that is, current flows into the load is equals to VL divided by, that is current I is equals to V divided by RSC plus RL. So let us take this equation number 1 from voltage source. Similarly, we can write for the current. So here the current in load, current flows to the load, that is I is equals to total current into opposite resistance, that is, here we are using the current division rule, so that is opposite resistance divided by sum of the resistances. So this is second equation. So in source transformation technique, just now I told that condition here. So the condition must be same, it has to be same load resistance and it has to flow the same current, okay, between these two terminals. Okay. Now equate the equations 1 and 2, then we are getting as VL divided by RSC plus RL is equals to I into RSH divided by RSH plus RL. So if we can equate the denominator terms here, then what we are getting here, so that is RSC plus RL is equals to RSH plus RL. So RL gets cancelled here. So then series resistance is equals to shunt resistance. Series resistance is equals to shunt resistance. So that is the one conclusion we got here. So next one, from the numerator we will see that is from the numerator we can say V is equals to I into RSH. So if you can substitute RSH is equals to RSC, then that is V is equals to I into RSC R. So from this we can write as I is equals to V divided by RSH. So from these relations, if you can convert from voltage source to current source, so then what is the current here? So from this relation, current I is equals to V divided by RSH. So from this we can say that current I is equals to V by RSH, whereas the RSH is equals to RSC. So this is the conversion from voltage source to current source. So that is this current I equals to V by RSG and this RSH is nothing but RSC. Similarly, if you can see for conversion from current source to voltage source, so if you can convert from current source to voltage source, then so V is equals to I into RSH. So from this relation, V is equals to I into RSH, whereas RSC is equals to RSH. So this V we can see here. So V is nothing but I into RHS from this current source and RSC is equals to RSH from the current source. So this is the source transformation technique. So we can use this technique here. So here in this case we can see here. So practical voltage sources are connected in parallel. So when practical voltage sources are connected in parallel, first we have to convert this voltage source into current source. This is the current source. And the second branch voltage source is converted into the current source. So that is voltage source is converted into current source and voltage source is converted into current source. So then according to the conversion, we will say that the currents in the parallel circuits is I is equals to I1 plus I2. So irrespective of their voltages across that one, so that is I is equals to I1 plus I2, whereas R1 is the two resistors are connected in parallel, so then R is equals to R equivalent is equals to R1 plus R2 divided by R1 plus R2. So after simplification, so again we have to convert this current source into equivalent voltage source. So then we are getting this voltage source. So that is I into R1 that is equals to R. So this is the practical voltage sources are connected in parallel. Similarly, if ideal current sources are connected in series, so irrespective of this terminal voltages here, irrespective of voltages across the sources, then the current is equals to, so because here in series the current will be same, so the total current is equals to I1 is equals to I2. In such cases it is not possible. So however, so we can treat that as I1 is equals to I, then the current in the line is I. Similarly, if we can see for the practical current sources are connected in series, then we can see we have to convert this current source into equivalent voltage source first, and this current source into equivalent voltage source. Again, we have to add up these two voltage sources. So these are the two practical voltage sources are connected in series, as we see in the first case. So voltages are added up and resistance is also added up. So finally, again we have to convert this voltage source into current source. So then this is the case here. So these are the ideal voltage sources. So if ideal current sources are connected in parallel, so sometimes okay, right. So if ideal current sources are connected in parallel, so then we can see here. So here the net current is equals to between these two terminals I1 plus I2. For example, if we can say that, we can also say that is I is equals to I1 minus I2 when I1 is greater than I2, or I2 minus I1 when I1 is less than I2. So here we can see that the direction. So if it is higher than this one, then we can go for the I1 minus I2. The net current is I1 minus I2 in the parallel branches. Okay, so similarly, if two ideal current sources are connected in parallel, so you can see these are the two ideal. The single equivalent current source is given here. So practical current sources are connected in parallel, then this is the equivalent value. So that is I is equals to I1 plus I2 and R is equals to R1 plus R2, R1 R2 divided by R1 plus R2. Okay, so this is about the energy sources and source transformation techniques. Thank you. So we'll continue next class.